Good morning, students. Hello, everyone. Today, today on 9th March 2021, we all are here back again to continue with subject physics. To continue with subject physics. Today, we are starting the new chapter, chapter number 11, which is based on the concept of current electricity. So, we will continue with new chapter, chapter number 11 from the book on page number 207. As the name suggests, current electricity means we are dealing with the behavior of electric charges, charge particles which are in motion. We can observe motion of charged particles either of ions. The ions are of two types, positive ions, negative ions, as well as we can study the motion of charged particles like electrons. So motion of ions and charged particles like electrons, protons, etc. can be studied. This motion of charged particles is observed in space or in vacuum as well as through material medium. While dealing with this particular chapter, we will concentrate the motion of charged particles through material medium. We will consider the motion of simplest case electrons. These electrons are readily available and hence we will study motion of charged particles electrons through material medium. There are different material mediums. The motion of electrons can be observed through different material medium like different electrolytes or like different metals because these materials have their own properties. Few materials are superconductors, few are highly conductors. Few material media do not allow the flow of electric charges through them. They are called insulators or bad conductors of electricity. We will concentrate or focus the motion of electrons through material which is highly conductive. For example, different metals, and these metals are called good conductors of electricity. Motion of same type of charge carriers in one particular direction constitute which is called electric current. So in this chapter especially we will study flow of electrons through conductors which has good conductivity for the motion of charged particles. So as the name suggests, we will continue to study the motion of electrons, charged particles through conductor. When that motion is unidirectional at in one particular direction, it will constitute current, and hence our focus is to study electric current through conductor. So material which allow flow of electrons easily through it is called good conductor of electricity. For example, different types of metals. In the metals, free electrons are readily available. What are free electrons? They are conduction electrons or they are valence electrons. The electrons lying in outermost orbits, which are loosely bound with nucleus of the given atom, are called free electrons. They are not bound with one particular atom. They are able to change their position from one atom to another atom, and hence free electrons are called conduction electrons. In metals, the motion is observed of these free electrons. In metals or in good conductors, these free electrons are available in large number, and hence we will move further to study the behavior of free electron. What is the behavior? Free electrons always behave like gas molecules enclosed in the vessel. If I have the enclosure in which gas is filled, the molecules of gas are bound to the enclosure, but each and every molecule has random motion. It moves in any direction, in all possible direction, with any possible value of velocity. Similarly, free electrons in metal perform random motion. They don't have any fixed velocity, they don't have any fixed position. They can move in all possible directions, but they cannot leave the conductor. They cannot escape from the boundary of the conductor, and these are called free electrons. So at normal condition, if you consider a piece of conductor, suppose metal rod of length L, and everywhere its diameter, cross section area, is same, then such is called uniform metal rod. So you select a piece of good conductor of electricity which is uniform and has definite shape. So what will happen at normal condition? Different free electrons available, they are able to move any possible direction, anywhere, with any value of velocity. So there is no net flow of these electrons in one given particular direction, and hence you never get net current. So net current under normal condition through the conductor is always zero. If you want or if you force these free electrons to move in one particular direction, then they will constitute the current. Along with this random motion, they will be acted upon by some external force, and the motion will be combination of these two: random motion, natural random motion, and the other, the motion acquired by electrons forcefully under the action of external certain force. So to channelize these free electrons in one particular direction, it is essential to have potential difference across the two ends. And you can set potential difference across the two ends if electric field is applied across this conductor, or the conductor is placed within the electric field or in the region where electric field is already existing. What happens? These free electrons, under the action of the electric field applied, acquire certain force. They will experience certain force, and along with random motion they will perform one more motion simultaneously, which is the impact of applied external electric field. So they will perform combined motion, and that time what happens when you apply electric field? The electric field means what? You get potential difference. This electric field can be set up with the help of source of EMF. Using source of EMF, one end is made at higher potential with respect to other end, and you get potential difference across the conductor. The here what happens, these electrons, each and every free electron experience force, like we studied electric field. Electric field, in that electric field, if you place any other foreign charge, it experiences force. So each electron will experience force, and they will get drifted towards the higher potential terminal. All these electrons will get channelized, and they are forced to move in one particular direction. So motion of all these electrons in one particular direction will constitute the current. So with the application of potential difference with the help of electric field across the conductor, you can have electric current through this conductor. When they are forced to move in one particular direction, their velocity do not remain constant. They do not have constant velocity, because when they move, they will collide with the localized atoms inside the material medium. So they will perform different collisions. Between two successive collisions, their path will be straight. But after collision, each time they may change their path, also they may change their velocity, and average value of velocity is called drift velocity. So they get drifted forcefully with drift velocity in one particular direction, and we get production of electric current. Electric current developed across this if will be momentarily, if for the instant you apply this electric field. Means what? If I keep switch over here, momentarily, I will close it. I will let for a short time to produce potential difference across these ends. Then momentarily, every electron will acquire drift velocity, and all these electrons will move from negative terminal towards the positive terminal. So motion of electron is against or opposite to direction of electric field applied. So actual current is flowing from lower potential to higher potential. But we always observe flow from higher potential to lower potential. We have never heard the motion from lower level to higher level naturally. So conventionally, the flow should be from higher potential to lower potential. So direction of conventional current is again opposite to direction of actual motion of electrons constituting the current. Conventionally, the current in the circuit is said to flow from positive terminal to negative terminal through the conductor. So henceforth, we will consider while studying the conventional current, direction of conventional current, even though the current we are getting due to motion of electrons which are moving in opposite to direction of applied electric field, against the direction of electric field. So this strength, I already told you, if you press this plug momentarily, if you produce potential difference for the movement across the conductor, for that particular moment, all these electrons will get drifted, and you will get production of electric current only for that particular moment. But here, what happens if you want continuous current, steady current? Then you have to keep potential difference between these two constant. Then and then only steady current is possible. So what is done, especially when you want to observe steady current? Then we have to keep constant potential difference. We have to maintain constant potential difference across the end of the conductor. So now we will assume the current is flowing steady of constant magnitude through the conductor for given time or for indefinite time, and we will keep this potential difference using this source of EMF maintaining on. So now we'll proceed further, assuming the current flowing through the conductor to be steady, and then we will study the behavior of the electrons. So current steady, it flows through the conductor by maintaining constant potential difference across its ends. The strength of this current depends on different factors. The strength depends on value of PD across the ends of the current, that is first factor. Also it depends on nature of the material medium. If you apply, suppose for the given material medium, this is copper. If you select one more wire of same length, of same diameter, only changing its material, suppose of gold. If you apply same potential difference, suppose potential difference is of V volts, we will apply same potential difference here also. So physical conditions we are not changing. So for same potential difference through this material, the value of I, and through this material the value of I are observed different. In this, for same potential difference you will get current I1, and for this piece, for same potential difference maintained across its ends, you will get current I2. They are not equal. So each material has its own ability for the passage of electrons through it. For the passage of electrons through it. And hence, the current produced also depends on the nature of good conductor. If material is changed, the current flowing for same potential difference also changes. So the strength of current depends on PD applied across it. You for given, suppose you select any one conductor. It is experimentally observed, if potential difference of volt V is applied, initially you will get current I. By not keeping all these physical conditions constant, if potential difference is now made V1 and assuming V is greater than V1, it is observed experimentally, current through it now will become I1. Naturally, value of I1 is experimentally found greater than I. If current is voltage is increased from V1 to V2, increasing, it is observed the corresponding current I2 for voltage V2 also increases, is greater than I1. So the relation between potential difference maintained with current is proportional. If V is increased, I is increased. That time you are not changing the physical state of the conductor, neither its temperature, nor its length, not its diameter, not its material. Then and then only, if PD increases, current through it increases. But it is not possible to get current I2 when you apply voltage V. For particular value of voltage, you will get particular value of current. Means what? If I want the current I2 to flow through this conductor, and if I maintain potential difference of V volts across its end, then you will never get current I2. For voltage V, you always will get current only I. This is the limitation. The material limits the current through it for given value of potential difference. For given value of V, the current flowing through it has a constant value. You cannot increase the current for same value of potential across the given conductor, and hence you will get certain opposition. Means what? Here, if I is not increasing, the number of electrons per current is number of electrons per unit time crossing the given area. Suppose 5 electrons cross this area. When V potential difference is applied across the ends, to increase the magnitude of current, number of electrons per unit time through the given area should be increased. But for given value of V, it is not possible to increase number of electron crossing the given area per unit time, and hence it limits the value of current. For given value of voltage, certain value of current is only passed through the given conductor. Means what? It checks the value of flow of charges through it. It limits the value of number of electrons flowing through it in the given time or per unit time. Hence, you will find relation between PD and I. Relation between potential difference and I is studied by scientist Ohm, and he stated his law, Ohm's law, in current electricity, which is fundamental law of current electricity. Hence, we'll proceed further to study Ohm's law in electricity. So, according to Ohm, I already told you, when all physical conditions of the conductor kept constant, current flowing through the conductor is proportional to potential difference applied across its ends. So, I is proportional to V. So, with the same, I could write V proportional to I. So if I take ratio of V to I, it will be certain constant, and this constant is called resistance of the given conductor. This value of R for given specimen wire is same. Means for given length L, for copper of same area of cross section, resistance is R. If you take another sample piece of copper wire having same unit cross section area, but length is changed. Now I have made length L1. Then its value of resistance will now become R1. This R is macroscopic quantity. It depends on several factors. So this R is expressed in terms of ohms. If V is 1, I is 1, R will be 1. So the resistance of given conductor is said to be 1 ohm if by the application of 1 volt across its ends, the current flowing through it is 1 ampere. So 1 volt upon 1 ampere is 1 ohm, or is recorded in terms of SI unit, ohm. The reciprocal of resistance is called conductance or conductivity. So conductance is then 1 upon R. I have telling you, we will select the material for the passage of electric current, which are good conductors of electricity. Then when we take different good conductors, different materials of good conductors, it is observed For few materials, this Ohm's law is strictly obeyed. So if you increase the value of V in steps, value of I increases in the same proportion, and the graph of Vi against V comes a straight line. Such are called ohmic conductors. For few materials, initially when V is increased, I increases. But after certain limit of V, if V is increased, I does not increase in the same proportion. Instead, you will get the behavior deviation. Initially, they are acting as ohmic, and after certain limit beyond certain value of V, the current doesn't increase in the same proportion with increase in voltage. Such are called non-ohmic. The graph then will become parallel, nearly parallel with x-axis, with voltage axis, and thus it's called non-ohmic conductors. So we limit our discussion for ohmic conductors only while dealing in this chapter. So from next time or in next time we'll continue with the property of these ohmic conductors. We are winding up the meeting. Thanking you all. We'll continue the same topic tomorrow. So thank you. I am closing the meeting for all.